Okay, guys, so last time when we started, we learned that we can make alcohols in two ways as we like. We can get exact multiplic of addition. Basically, I only focus on the two vinyl carbon, not neighboring group. We can do oxymethylation, demethylation to get the desired alcohol. The most substituted without rearrangement. I hope you notice I said the most substituted, not the most substituted. Naturally, the most substituted always means rearrangement. The most substituted basically means we are focusing on the two vinyl carbon. Yes. That is the only time we use that is we are not going to be worried about carbocation rearrangement. If there is ever a possibility, of carbocation rearrangement to produce a different cation, and by different cation, I just don't mean going from secondary to tertiary, guys. I mean going from one secondary to a different secondary. Acid catalyzed hydration of alkenes does not have any research value in organic lab. In industry, because they do at very large scale, they can isolate different compounds and sell them, that is not a problem. Organic lab, if I get several different products, and the scale that we do is worthless. And so acid catalyzed is not the most popular. The only time it is being done, this is no problem. I can do acid catalyzed because any carbocation that I get is exactly the same. So even though there is a rearrangement, regardless of how I write it, I still call it cyclohexanol. So if you get only one product, acid catalyzed is the best option. That when you can get more than one product, acid catalyzed never is going to be the choice. So then, depending on whether I want more substituted or less substituted, I will do. For more substituted, oxymethylation, demethylation. For less substituted, we will do hydrobolation, oxidation. Now, with oxymethylation, demethylation, we learned when we are getting a stereocenter, it can go from either direction, guys. When water was attacking, it could attack from either direction. Now, when it comes to hydrobolation, so now we are talking about a stereochemistry of hydrobolation oxidation. Now, when it comes to hydrobolation oxidation, not only it has a regioselectivity, which it means the OH will go to the less substituted carbon, it also has a stereochemistry. What do I mean? It also has a stereochemistry. If you look at the first step of the reaction, you saw how H3B was added, guys. How was it added? Boron and hydrogen. Both were added from same side of carbon-carbon double bond, which we call it syn addition, from same direction. What am I going to touch is, let's take one methyl cyclohexene and react it. Oh, I changed my mind. Okay? So, because I want to obviously explain the stereochemistry. Now I'm curious, I want to name this compound. Okay, first, I'm going to label carbons randomly. I'm going to label, not number. And again, I repeat, it's randomness because I don't want to give any clue. Which carbon will be atom number 1? Excellent. No. Why not? Lowest possible. So lowest possible between B and C, which one should be? B. Because B is also more substituted. Is that right, guys? Lowest possible number on functional group. Your functional group anyway is going to be 1 and 2. But 1, also your substituent has the lowest possible number. So now that we have numbering, what is the name of compound? You have to assign the stereochemistry. But you have to assign the stereochemistry. Carbon that is, now I'm going to label it. Carbon number 5 is a stereochem. So you have to assign the stereochemistry to that carbon. Yes. Who cares about substituents? Functional group always would have lowest possible number. So the functional group that is 1 is the most substituted functional group. Those two have to be 1 and 2. So the one that doesn't have any substituent and the one that has substituent, which one would get lowest number? Don't forget, guys, you always focus on functional group. You want to assign lowest possible number to functional group. Cyclic molecule, lowest possible number always is number 1. Okay, so that's it. Okay, now, carbon number 5, is it R or S? It is R. So, the name of the compound, it won't make any difference whether you say 5R or R. Then what? Go ahead. Listen here, if you want to say it louder than this. Okay? Don't forget alphabetical ordering.
5-isopropyl.
That is not isopropyl. Absolutely. Whether you say tertiary butyl or 1,1-dimethyl ethyl. Agree, guys? So whether you say 1,1-dimethyl ethyl or of course, no, because it is complex substituent. Or then, when it comes to this complex substituent, it is going to be 5 because it is attached to carbon number 5. Whether you call it 1,1-dimethyl ethyl or tertiary butyl. The first letter is before M. That's why it is going to be 5,1,1-diethyl methyl or 5 tertiary butyl. Then 1 methyl cyclohexene. So, now I'm going to add, of course, that was not the purpose of writing the molecule, that I realize not that I am writing. It's better I test you on your nomenclature to make sure that you do remember. So we are going to do hydroboration, and because I don't want to use BH3, because BH3, remember, reacts with 3 alkenes. It has 3 hydride. So I am going to use, these substituents are commercially available. Okay, let me see. So I am using, obviously, a hydroborane that it has only 1 hydrogen or deuterium. It won't make any difference. So this one is going to be 1 to 1. And obviously, don't forget I said every time we are doing this, It has to be in presence of ether. This is hydrobolation step, followed by our oxidation, which we need hydrogen peroxide. The whole idea is to add water. Last but not least, it has to be done in basic medium. So it is obvious that this time we have D and OH. I am not putting charges on them. You do understand that these are the ones that you will see in final paragraph. Okay. Now that we know we have this, now the question is, first, which of the two atoms get D, which of the two gets OH, guys? Absolutely. Carbon number 2 gets OH because we call this reaction anti-Markovnikov. Now, the question is, what is a stereo relationship between the two groups? Both are going to be added from the same side. Syn means from the same side. Now, that both are going to be added from the same side, then the question is, what will be the relationship with this bulky group? Are they going to be added from the same side as bulky group or opposite? It's going to be opposite. So, so this is as far as hydrobolation oxidation. They are stereo and regio. You would expect the addition always be done from the side with less steric hindrance because of the throbbing during transition state. So these are hydrobolation. The next reaction that I'm going to talk about is addition of carbene. In the first place, what is a carbene? Carbene, believe it or not, is an analog of borane, BH3. Remember I was talking about my colleague that was doing research with boron for 10 years and really couldn't get that far. That is not true. We always learn. So one thing that we learned, we cannot make boron to act like carbon. But on the other hand, carbon can act like boron. So carbene is an analog What I mean, both atoms have sp2 hybridization. Both atoms have 6 valence electrons. Both atoms are highly electron deficient. So, when we are talking about carbene, that's what we are talking about. Electron deficient species. Now that being said, because carbon always likes to have 4 covalent bonds. Don't forget. You never ever see carbon doesn't have formal charge. 6 derivatives. So these species are only being prepared during the reaction, and they are being used instantly. One of the species that can be used to produce carbon is diazomethane. And hopefully in CHE118C, which very soon is coming, you do remember, guys, because I will talk about this. First, it's not a secret, I'm teaching 118C. And I'm going to tell you, we will talk about diazomethane. We will talk about its preparation, those kind of things. Now, when it comes to diazomethane, then azo is which atom? Yes. You have seen azides as excellent nucleophile. What were they? N3 minus. Azide is N3 minus, guys. Excellent nucleophile. For example, sodium azide, because azide doesn't exist again. It's an anion. Doesn't exist on this one. So when it comes to diazomethane, it is CH2N2. Now, one of the Lewis structure of CH2N2 is that's one of its Lewis structure. Obviously, you can draw resonance. Now, I want to ask you guys, again, now I have resonance. Of these two resonance contributors, which one would you expect to be more important resonance contributor? The top or the bottom? The bottom. Why? Absolutely, compatibility of charges. You want negative charges on more electronegative, positive charges on less electronegative. But nonetheless, the contributor that undergoes reaction is this one. So when we react, before I continue, I honestly am realizing that I have to explain more. Review chemistry, your organic chemistry. So this is throwing me down, guys, in CHE118B, and I have to get to Robinson annulation. There is no option. Even though I am teaching the class, in the future I cannot forgive myself for not getting to the point that there is equilibrium. Some of you don't need any further chemistry. So because of that, I need more time. You know, I can go very fast. And due to your interaction, I am realizing more explanation is required. Is there anyone that cannot stay 10 minutes longer each lecture? I am willing to volunteer my 10 minutes. No extra charge, I will not send a real bill. So I am willing, because honestly I have, I am teaching, I have get I know as today where I should be, and I'm not at the place I should be. And because I am noticing, we need to live. And I have talked to Dr. Mascot, and he was next, came to me and asked me, and somehow he feels that you guys need more explanation because he was not able in such short 6 feet to cover, and CHE118A is, principle of 118 nomenclature you just saw. It was important, because in 118B, we assume you have seen the principle, we just talk about the functional group, that's it. A becomes in, A becomes all, A becomes all, that's it. That's what we give state. But it's obvious we need more. So from now on, I will continue until 950, guys. So keep in mind that. Now, that being said, I was going to say that when it comes to these compounds are being used to make cyclopropane. And I am using the resonance contributor that gets involved in reaction. First, I want to ask you, will you consider this reaction regioselective? Absolutely not. Both carbons get the same atom. This is your electrophile. Don't forget the nature of chemistry of carbon-carbon pi bond. Electrophilic addition. Well, this is your electrophile, even though that you have a negative charge here, guys. Because you know nitrogen is not happy to be positively charged in presence of this electron negative. Second, we know anytime that we have a group that can live as a gas, that reaction is spontaneous, one-way reaction. So another case of electrocyclic addition, you give with one hand, you take away with the other hand. So what will happen? So I give electron with one hand, I take them away from the other hand, which it means naturally I am writing over CH2 here. These reactions always are syn addition. Basically, it means CH2 is being added Does this one look like cyclopropane to you? Okay, guys? So, it is always syn addition, because there is no other way. You cannot twist it around to go from the other direction. Now, that being said, it happens that diazomethane is very explosive. And unfortunately, scientists that they have tried to do the reaction at large scale have lost a member of their body. Unfortunately, I'm serious. Or it is highly explosive. So it can be done only in small quantity. This is not a reaction that they can do it in industry to make cyclopropane. Only millimoles scale. which obviously does not have that much value. The only good thing about it was and is, at least gave us the courage, that we know still it is possible to make a compound that is not very stable. I guess I don't have to remind you that cyclopropanes are very unstable. So here we are making a very unstable compound that still we can do it. But it happens that there are compounds that they have cyclopropanes, and we need large scale. So two scientists were able to establish the reaction at large scale based on the understanding and the concept of having the ability to produce such a thing as carbene, guys. Again, I want you to focus on the active ingredient. So the way that science read it, they are using, obviously, diiodomethane, which is very stable compound, is not explosive at all. Now, I have to have the ability to produce 2 electrons. So what they did, they used from your general chemistry, you may remember zinc is very reactive metal. So basically they used alloy of zinc, copper alloy. Copper is not very reactive. Do you remember that? Zinc is very reactive, copper is not very reactive. So zinc has the ability to give 2 electrons, so the iodide leaves. For this reason, but this time I'm not showing you stereochemistry because it is obvious that what will happen basically it is based on the principle of redox reaction. Your zinc is being oxidized and your obviously molecule is going to react. So this is as far as making cyclopropane. Now, on the other hand, if we want halogenated cyclopropane, that is possible as well. How that will be done? Oh, by the way, any hollow form. Now, the reason that I say this is any hollow form, this, except for which halogen? Fluorine. Remember, we don't use. They say you can use CHE118B, you can use CHE118B, any of those. If you use them in strong base, either sodium or potassium. By the way, originally it was used in presence of sodium hydroxide. So with sodium hydroxide, it has worked as well. The yield was not that high, because you could do SN2 substitution as well. But with tertiary butoxide, you expect a lot less substitution. So that was done, and the product reaction. First, we will look at the mechanism. To this hydrogen, as you would expect, is fairly acidic hydrogen. Well, it is fairly acidic hydrogen gas. Those electronegative group are taking the electron away, so it is acidic. Now, that naturally makes your carbon to be highly electron deficient. That makes that hydrogen deficient. And that's why I said, with hydroxide, you can also have SN2 reaction. The tertiary butoxide, you are not going to get that much SN2. You are going to have elimination. So you are getting a dihalogenated carbene, for which dihalogenated carbene will react exactly again. I repeat, you are giving electrons with one hand, you are repelling them with the other hand. So these are as far as formation of dichloropropanes. The next reaction that we are going to talk about is halogenation. Now, when it comes to halogenation, you can guess any halogen except yes, polar solvents. So we do need polar solvent to do the reaction. Question. Can I call this reaction regioselective? No. Absolutely not, because again, each carbon gets the same thing. So it's not that your electrophile prefer one thing, your nucleophile prefer another thing. Yeah. Both electrophile and the nucleophile are getting same thing. So that's the reason that it is not regioselective, that it is stereoselective. Yes. Okay. Dipolarimeter, I said polar solvent. When it comes to this reaction, because guys, again, when it comes to dipolarimeter, you cannot see it as electrophile. The chemistry of carbon-carbon double bond is electrophilic addition. That's why that is only solid. When it comes to the reaction, it is always n-type addition. So first, as you heard me, I said we are using either Cl2, Br2, or I2. What's the difference between these three halogens and fluorine? Guys.
Not very picky about what it reacts with.
Well, that would not be a problem then.
Oh, never mind.
What's the difference between the three halogens that we put them in one group and fluorine? That is an element all by itself. They are polarizable. Due to their size, they can be polarized. Whereas fluorine is too small to be polarized. So, what is happening? General chemistry, you have such a thing as van der Waals forces. Do you remember, guys? One of those van der Waals forces was lambda. Lambda is instantaneous dipole-dipole interaction. Instantaneous, not permanent dipole-dipole. So here, obviously, you have two non-polar species, you are bringing them together. Okay. But what will happen, you know that pi bond is source of electron, you know like charges repel. Is that right? So what will happen, when the pi bond comes close, it makes your non-polar species to become polar. That's why we call it instantaneously, momentarily. And don't forget, again, the nature of chemical reaction always, for carbon-carbon pi bond is electrophilic addition. It must start with electrophile, otherwise it wouldn't work. So this is the reason that you do need, first, polar solvent that makes your halogen to be polarized. Second, you need a halogen to be polarizable. If it's not polarizable, it cannot work. So what will happen? Again, another case of you are giving electron with one hand, you are taking it away with the other hand. Now, I want to notice something. Did I get a carbocation? So, would I ever expect rearrangement? No. So it doesn't matter. Even if you had neighboring methyl group, you wouldn't have rearrangement. It is polonium ion. Your halogen is positively charged, not your carbon. No carbocation, no rearrangement. Now, obviously, you have seen this analogy yesterday. When I say you have seen this analogy yesterday, what do I mean? You saw. Where did you see similar situation yesterday? Oxymercuration. You had mercury that was positively charged. and three-membered ring, which it means very, very unreactive. So when the halide comes, it comes from opposite side. Exactly like SN2 reaction. Now, this is something that truly has been experimented. What do I mean? It has been experimented. The good thing is, as you know, in OCHEM, we have such a thing as diastereomers when it comes to alkenes. For example, 2-butene. You and I know 2-butene could be cis or trans. Okay. Now, both of them react with halogenism. Of these two, only one of them produces optically active molecules. The other one does not. Okay, guys? When we do halogenation, one of the diastereomer produces optically active compounds. The other one does not. Now the question is, which one? And I have to tell you, in organic chemistry from now on you will see, when we are doing reactions only for the purpose of diagnostic, to say, for example, if I want to know whether there is carbon-carbon tie bond, we will use boron, not chlorine or iodine. We will use boron. For this experiment, except again, when I want to find out which of the two compound it will produce optically active molecules, I use boron, not chlorine or iodine. When is that? When it comes to reactivity, in this case, truly, it is difference maybe in second, maybe. They all are reacting so fast that it is difficult to measure rate of reaction. So why bromine is more preferable? Chlorine is poisonous gas. Iodine is solid. Again, all of these are harmful anyway. But that's why you are using a little bit very dilute acid and iodine solution when you have wounds, guys, because they kill the bacteria. But that is very, very low concentration, very small quantity. So, bromine is liquid. Because it is liquid, it is easier to handle. This is one. The second, I don't know, have any of you have seen bromine to know what color it is? When it comes to bromine, it is a kind of, I will say, berange solution, and that's what it is, literally. Brownish, purplish solution. But when you get hollow alkane, it's clear colorless. And this is, I don't know if you have done your unknown or not, in lab, the very first experiment we do to find out whether there is carbon-carbon tie bond, adding the bromine solution. If your compound has tie bond, the instant that bromine touches your compound, guess what? Color disappears. So that tells you have tie bond ties. Now, that being said, now the question is, how can I find out which of these two will produce optically active? Which one that's now? Then, again, I'm going to tell you something that I said the other day. Remember the other day I said, we understand these are planar sp2 hybridized, no stereochemistry, flat as pancake. IBG guys? That, for the purpose of understanding of the reaction, we can use our imagination, which is truthful. What do I mean? You are not using this, so it's better. Thank you. So, this is my molecule. Is that right? It is flat as pancake. Can I assume that I am looking from this angle? Or from this angle? Yes. Can I do that? Why not? Yeah, no, I'm saying that molecule doesn't change, but you can look around it. See, if you are looking and you were drawing, wouldn't you show, yes, wouldn't you show these ones are coming towards you? And the ones that they are coming toward me, wouldn't you show that? So even though it is flat, for the purpose of understanding, I can use that. So I would assume that when it comes to this molecule, so you get the idea, you are looking from the other side, is that right? And when it comes to that one, again, if I am looking, so here I am adding bromine. So obviously bromine is going to be added n-type, is that right? So they have to be 180 degrees apart. Now I'm writing my CH3 because I'm going to ask you. Okay. Assign R and S and tell me whether this compound is optically active or inactive. What is the stereochemistry of this carbon? What is the stereochemistry of this carbon? Is it optically active or inactive? It's not active. It is
Inactive. Oh, sorry.
no, you are correct. It's inactive. And what would you call it? What is the compound that it has stereocenters? Stereocenters, because obviously it has two stereocenters. It's not optically active. Meso. Okay. So this one, as you can see, is meso optically inactive, which you can guess. What is the stereochemistry of this? Yes. Agree? So if you have R, what else would you expect? SS. Don't forget, again, IGP. Because I have written this way. Couldn't I put we are there, which gives me SS. So keep in mind, I said, if you are generating a stereocenter and your molecule is not meso, you would expect either diastereomer or enantiomer. In this case, you would expect enantiomer because that is not any pre-existing. So this is as far as halogenation. Now, let's look and understand halogenation one more time. When it comes to halogenation, as you see, we do the reaction in 2 steps. Is that right? Step 1, we are adding electrophile. What do we do in the next step? We are adding nucleophile. It is 2-step reaction. It's not 1-step concerted reaction. What it means that when it comes to halogenation, the halide is not the only nucleophile I can add. I can add a whole bunch of nucleophile, such as water, alcohol, you name it. Any nucleophile, guys, any nucleophile that you have seen in CHE118A, you can add here. By that I mean cyanide, azide, a different halide. For example, one has chloride, the other one bromide. Okay, guys? So basically, I can make it regioselective as well by mix matching. So, the fact that I can use different halide, one of those that is very, very popular in organic chemistry, one of those nucleophiles is, believe it or not, what? So what I mean, you all know, both in industry and organic lab, epoxides are very popular. Mother Nature does not make epoxide. So hot epoxides are being made. Going back to our CHE118A, guys, do you know how to make epoxide? So I give you going back to CHE118A. Do you know how to make ethers? It is a very well-known named reaction. What am I talking about? Williamson ether synthesis. Have you heard that? Okay. In case of Williamson ether synthesis, you would take your alcohol, you would change it into alkoxide, you would take a second molecule of alcohol, you would change it into haloalkane. Then you would under SN2 condition. When we are saying under SN2 condition, what do we mean, guys? Could your R be tertiary? Absolutely not. Primary is preferable. Secondary, if you have no choice. Absolutely never tertiary, because you are going to get elimination. Now, of course, I used same alcohol. That it doesn't have to be same alcohol, remember, because these reactions are being done in different steps. So you can use different R groups, make whatever ether you want. So this is the most popular way of making alcohols. That's why after centuries still, it has a name. And still it's being used to make ether. Now, this cyclic molecule, obviously with epoxide, first what is epoxide? Epoxide is trimembrane. Okay? So, what it means? It means that I must have both functional group on the same molecule. The functional group alcohol and haloalkane. I must have it on the same molecule. So when it comes to epoxide, basically it means I do need a compound that has both functional groups. The halide and the alcohol. Now, the only difference is this time I don't have to use such a strong situation to make the alkoxy group gas. Here, due to the fact that the presence of halogen makes your hydrogen more acidic. So it's easier to take it over. And the second, due to the fact that the two reacting parties are very close, you expect collusion right away. So when it comes to cyclic, I can use sodium hydroxide to do the reaction. And again, I repeat, when it comes to epoxide, you have heard their name over and over. And in organic lab, they are very important as well. Now the question is, how can I have this compound? One thing I'm going to tell you, Mother Nature does not make any halogenated compound. You cannot find any natural product that contains hydrogen, chlorine, bromine, or iodine gas, or fluorine for that matter. Mother Nature does not make. We have to make it. So, for this reason, the mixed electrophilic addition of halogen in water in organic lab is very popular. What I mean is, if I take a halogen, instead of using CH2Cl2 as solvent that I used. Remember? Instead of CH2Cl2, if I use water, I will get something about that. 80% of the product is this, guys. Which you can guess. What would be the other 20%? Dipolo. Which it is, if you consider it is good. Of course, I cannot get rid of that. And it has a few other problems as well. That, for now, I want you to know, this is very popular. So that being said, first, even though you know the mechanism, I will write the mechanism.
You said dihalo, right?
Thank you. Thank you for, no, I know what you are. Thank you, you're correct. That's what I said. Thank you so much. So we will look at the mechanism. Step one is exactly the same way as you see it. And the only reason I am doing it because I want to practice mechanisms. Understanding mechanisms are important. Now, when it comes to the next step, obviously, as you see, your polonium ion now has choice. Either water can attack or another halide can attack. And one thing that in the past students have asked me, they have said, if my halide was boromide, for example, obviously boromide is much better nucleophile than water. So what should I expect? 80% of hollow hydrogen, and this class of compounds are genetically colorohydrogen, bromohydrogen, you name it. And so the question is, boromide is million times more reactive as a nucleophile than water. Why I would expect hollow hydrogen 80%, not less. The answer is that keep in mind that when I am about making this species, which it is very unstable, water is there. I could guess. When I am about to make it, water is there. Was halide there? No, halide forms when this is fully developed. So what will happen due to the fact that this species is very, very unstable? Beggars cannot be choosers. First come, first served. Water is already there at your service. So as soon as it forms, I want to see how I wrote it. Okay, so I put my Excel up there. So I put it here. And I guess I don't have to tell that as soon as this forms, your oxygen is going to be deprotonated. What is the best base? Water. It's already there again. Boromide is there, but if boromide reacts, you are still going to get HBr. What HBr does, guys? So, now, as I mentioned, now that I have hollow hydrogen, then this hollow hydrogen will go and form epoxide. So I'm going to show you mechanism of epoxidation. As I have said earlier, this hydrogen is more acidic than hydrogens of alcohols for obvious reason. The presence of electron withdrawing group increases the acidity. Your halogen is electron withdrawing group. It increases the acidity. So what will happen? This is something that you wouldn't expect to be favorable with normal alcohols. With normal alcohols, the equilibrium is more to the left. With this class of alcohol, the equilibrium is more to the right because of relative acidity. I guess I don't have to tell you that both nucleophile and leaving group are sucralose for comfort. So these are how epoxides are being formed. Now, again, I repeat, when it comes to epoxide, they have lots of use. This method, yes.
How about CHE118B?
That's what happened. You are just a few seconds after that. Epoxides are very popular. This method, several decades ago, was the only method that they knew how to make epoxide. But as you see, it has its own issues. What are the issues? First, as you saw from the very beginning, you have to be prepared. Don't expect more than 80%. Agree, guys? Because no matter what you do, dihalogenation still is there. And experimentally is about 20% of the problem. That's one problem. What is the second problem? I want to remind you that I am using base. Is that it? And as you see, you have halogen. Can I have elimination? Can I take a proton here? The carbon-carbon double bond? Absolutely yes. Why not? So another problem is that instead of making epoxide, I can make a new carbon-carbon double bond that I didn't want. So these are the problems. Of course, there are times that still this method is more superior than the next method that I am saying. But it is going to be for normal epoxide. Now, scientists have developed a better method that it can go only in one direction, and that is epoxy, nothing else. So, what is the alternative method? Is peroxycarboxylic acid. So the next method that I'm going to talk about is epoxidation. Using peroxycarboxylic acid. The first peroxycarboxylic acid that was synthesized don't forget peroxide bond. That's why we are calling them peroxycarboxylic acid. The very first peroxycarboxylic acid that was synthesized was methachloroperoxybenzoic acid. You don't want to spell that. Okay, guys. Commonly it is known as MCPBA, methachloroperoxycarboxylic acid. So when we react this compound with carbon double bond, when we are reacting this with carbon double bond, we will get the carboxylic acid itself. Okay. So we are extracting the peroxy oxygen, guys. So how does this reaction work? So I have to tell you, MCPBA was the very first one. And again, when you see here, anything you see, it means solvent. Guys, so I want to be aware. Because all chemical reactions occur in solvent. So I am using a generic also I will remind you that I am not showing the stereochemistry of your epoxide for obvious reason, because it could go from either side if there is not a steric imbalance. This is one. Second, obviously oxygen, both bonds are going to be from same side. It could not be possible that these two bonds to be parents. Would it be possible, guys? So that's why I'm not showing a stereochemistry. So how it works? Don't forget, the chemistry of carbon-carbon pi bond is electrochemical addition. Always starts
So this time, what is the electrophyol? You heard me, I told you we are going to extract the peroxide oxygen. So, from general chemistry, we are familiar with certain things as hydrogen bonding. If you have oxygen and you have hydrogen that is bonded either to oxygen or nitrogen, you expect hydrogen. This is one. Second, from CHE118A, we learned 5-member link, 6-member link are Mother Nature's favorite cyclic interaction. I don't know if the diagram that I have drawn gives you a kind of idea that they have cyclic interaction or not. I hope you are paying attention. Basically, this atom is electron deficient for obvious reason. So the direction of electrons are in this way. So this is going to be your electrophyol, guys, this oxygen. Because the nature of carbon-carbon pi bond is electrophilic addition. So what will happen? It is all a cycle of electrons. Your pi bond is taking this hydrogen because it is already. Your other pi bond is giving electron to oxygen, which is your electrophyol. So you are giving electron with one hand, you are getting it back with the other. Now that being said, again we all understand oxygen, nitrogen, carbon, all of these elements that they are in the second row. Maximum they can have how many valence electrons? In compounds, maximum how many? 8. They never ever can go over 8. Even oxygen, even fluorine, they cannot go over 8. So what will happen? Obviously, when you are taking the electron away, here, this carbon becomes electron deficient. This oxygen cannot have. So all is going to be a cycle of electrons that they are going around. That's why your peroxy acid becomes a regular carboxylic acid base. And the oxygen of peroxy is going to be inserted. Physically, you can see that oxygen is being inserted between the two vinyl carbons. Now, why epoxides are so popular, other than being used as epoxide, they have lots of use. What are the use of epoxides? Formation of vicinal diode. Vicinal means what, guys? Two atoms bonded. When I say vicinal diode, what do I mean? The two neighboring carbons have OH. They are alcohol. So, in lab, that we are trying to make natural products, to be more specific, carbohydrates. Because carbohydrates are molecules that we have two or more OH group bonded to vicinal carbons. So naturally, these epoxides are useful in making diodes. So next, the reason synthesis of N-type vicinal to make N-type, always, the two OH groups are in N-type position. When it comes to epoxides, you can add water in epoxides in either acidic medium or basic medium. Don't forget, water by itself is not GI. So either in acidic medium or basic medium, you can add water always N-type vicinal diode. The two OH are 180 degrees apart. Always N-type. So we will look at the mechanism to see why that's the case. So first, mechanism in acidic medium. This is what I am looking at. I'm going to ask you guys, what would you expect first? What would the first step? Acid-base reaction. There is one reaction in chemistry you cannot stop. It is possible. And that's acid-base reaction. Which in this case, obviously, it is possible. So, step one, acid-base reaction. Don't forget that. This is going to be the most unstable oxonium ion you could ever have. It is remembering and oxygen is positively charged. So what will happen then? It doesn't matter that you do not have a good nucleophile. And don't forget, when the leading group is present, the nucleophile always attacks from the opposite side. Now, that being said, before doing this, so the reason I wrote that, I want you see, from the very beginning, anytime, guys, anytime you open any ring opening, always is in what manner? Ring opening always is N-type. Ring opening is always N-type addition. So I want to know that. So it's not that you and I decide, and I will explain. I said this is the most unstable positively charged oxygen that you can have. In this case, I can have a secondary cation. So because it is very unstable, I will go ahead and force my cation. Question. If you have cation what do you expect? Rearrangement. This is the only cation, of course, this is not the only, this is one of the cations that cannot, will not rearrange. Okay? I cannot or will not rearrange. Well, let me tell you the story. As I told you, I have been around these atoms, these compounds, and they talk to me. So I know what is going on. When it comes to this oxygen, you will agree with me, oxygen is measurable. Agree, guys? Why oxygen is measurable? Positive charge, remember. Are these two carbons happy? Absolutely, they have huge angle strain. To be specific, you know, you call it ring strain. Do you remember ring strain? Remember ring, it is nearly 99% of ring strain in cyclopropane is angle strain, guys. You have huge angle strain. So you have 3 extremely unhappy parties. So they sit and they talk to each other. And they say, you know, we really like each other. We love each other. But this is a miserable situation. So they decided on a friendly condition, they split. So they get out of misery. But between you and I, oxygen has a feeling for that carbon. Okay? So you say, okay, I know you will be happier if I go. But remember, I am around the corner. Anytime you need me, call me. Okay? This is the reason that I call this cation assisted carbocation. It is being assisted by what, guys? Oxygen, remember? Anytime it needs, it can call. But, of course, carbon cannot sit forever and wait for that oxygen. Or it cannot call it all the time because, again, it's going to be all over again, wouldn't it, guys? Again, oxygen comes, again, the same story. So, obviously, a new person will arrive. A new molecule will arrive. Now, let me ask you, would the other nucleophile would ever dare just walk in front of that oxygen and make relationship with that? In over there. It will be punched in the nose, if not other parts. Very hard. So this is the reason that even though, as you will see, you have carbocation, you expect SN1 situation, don't you? You expect the new incomer goes from here. It cannot, because it cannot come from the same side of the other group that was there, was happy to have. For this reason, ring opening always is anti-addition. Ring opening always is anti-addition. So the nucleophile, which in this case is water, will come. Last but not least, again, I don't have to tell you that you are going to lose carbon. So regardless of whether you have cation or not, regardless of whether you have cation or not. The position of the new nucleophile is very clear. Question, is this molecule chiral or achiral? Is it optically active or inactive? It is chiral because it is RR. Which it means, what else should we do, guys? Allows enantiomer. Keep in mind, because again, there is not a pre-existing stereocenter. If there was a pre-existing stereocenter, then you would write Allows diastereo. So this is ring opening in acidic medium. Now we are going to talk about ring opening in basic medium. Now, when it comes to basic medium, I'm going to ask you, between water and hydroxide, which one is a better nucleophile? Absolutely hydroxide. Again, going back to chapter 5, if the attacking center is the same atom, a charged nucleophile is much stronger nucleophile than a neutral nucleophile. So either of the two compounds, oxygen is the nucleophilic center. A charged nucleophilic center is much stronger. So this time, what is happening? As you would expect, the hydroxide attacks, which this time is 100% SN2 condition. And because it is 100% SN2 condition, you would expect it will backside attack. And don't forget, water is acidic enough to peroxide. So base or acid are only catalyst because constantly are being regenerated. So these are as far as formation of epoxide and also ring opening of epoxide to make vicinal anti-diol. Now, that being said, also ring opening is regioselective, guys. Not only stereoselective. Stereo always is anti. Also, it is regioselective. I will give you an example. I will not go over mechanism because it is Chem 118A curriculum. In case you don't remember, then you can go back and review the mechanism, the understanding, even though the mechanisms are there, that in case you don't remember, you can go back and review. So what I am going to tell you is regio selectivity. Of the parcel. The monitor that so far I have been using would not have any radioselectivity because both nucleophiles and living groups are the same thing, and they can produce the same group OH. Now, I am going to use a different one. And also, I am not going to use water anymore, guys, because still water will give you 2 OH. You don't know which OH is your nucleophile, which OH is your epoxide, because you always get enantiomers. So now here I am going to use something different. Okay. And I'm going to ask you, write major organic parameters for this reaction. And also, same reactant, pretty much same nucleophile, again, I'm going to ask you write major organic parameter. I will wait 1 minute to see what it is. So, when it comes to ring opening, it is both a stereo and a regio. A stereo always nucleophile and a leading group, 180 degree focus. Regio, you have to remember about whether it goes by SN1 mechanism or SN2 mechanism. Acidic medium, obviously SN1. You get carbon. Basic medium SN2, naturally less hindered carbon, deeply bonded to nucleophile. So this is something that you need to review if you have forgotten. Of course, the mechanism here, you can apply it to see it for yourself. That in case you have forgotten, you have to go back there. Today, because I just said I will go 10 minutes and some of you were not here, I will stop talking about lecture, and tomorrow definitely I will go 10 minutes over. But I want to use my 4 minutes, I still need my 4 minutes. I'm not going to talk about lecture, yes. I'm going to talk about other things that I am getting emails, and I want to answer to those. So any of you that you need a next commitment you want to go, I'm not going to talk about anything that is related to lecture. First, textbook. The department had notified us from the very beginning that 8th edition will be offered during fall for CHE118A. So we are using 7th edition, which I have end chapter problems. I don't have end chapter problems for new edition because I even have not had chance to see it. But a copy is in Shields library. You can go and take picture if you have 8th edition. Second, you are sending email. How can I do there in OChem? And I'm going to tell you honestly, I have had so many students in my 118C that they got 7% on the first midterm, and they got 75% on their final. 3 of them came to my office and told me, all I have to tell you, okay, you have to learn it on your own, and you have to study it with others to get help. So, I'm going to tell you the way I was studying OChem. I always understood mechanism, yes. Because that's something that tells me what would I expect for paradigm. So mechanism understand. Reactions, unfortunately, are memorization. So I was making flashcards for reactions. And the way that I was making flashcards, I will give you an example. It doesn't matter in what order we done, and don't forget, because all of them are together. It's 2 steps, these 3 are together. So, this is my reaction, which by now you know the way it should work. Okay. Now, the way I was making flashcards for OChem, well, our generation, we didn't have prepared flashcard. So this was my flashcard. This flashcard has how many sides, guys? 4 sides, is that right? So, side 1, and I'm going to just label A, the whole thing B, and C. Okay? So one side, I call it side 1. Side 1. I would write A, B, question. Side 2. I would write A, C, question. Now you can guess what I would do with side 3. Side 3, B, C. Now, why I was making flashcard this way? because I always had to challenge myself to come with a part of things. If everything is in front of your eyes on your flashcard, you are not being challenged. You don't know whether you know it or not, because instead you think that you are studying, guys. Believe it or not, you are not questioning yourself. That's the... Now I still have one side left. What is the last side? Because unfortunately you saw most of the mechanism, and they do not fit even in half of it. Did you see hydrobolation? Can you read hydrobolation? Yeah. I can't. So I'm going to tell you. The side 4, I call it nodes. So by nodes, what do I mean? For example, regioselective. Is that right? I will remind myself whether it is Markov-Ikov or anti-Markov. Stereo selective, seen, anti. Or any other comments that I want to remind myself. So this is one. Second, when it comes to study, do in chapter problems along your step. Because those are the ones to get the point of what they have taught right away, so you know what this means. End chapter problem. Don't do problem 28, A, B, C, D, E in row. Why not? You get A wrong, you get B wrong, you get C wrong, all of a sudden F comes correct. I say, oh, I got it. No, you didn't. By default, 20%. Is that right? When you are doing end chapter problem, always make a quiz from end chapter problem. For example, problem 28, pick A, C, any. And keep record, guys. So pick a bunch of questions and give yourself reasonable time. Not all the time in the world. Don't forget, midterms are only 50 minutes. So answer, then compare your answer with solution. If you have it, get it. It is only one time. If you don't look at their response, or you know it is wrong. Go back to your notes, figure on your own why you were wrong. Honestly, if you do study this way, I personally do not know any student that has done it, and at least on their final they did not get B. They were pulled off their score. I'm talking about final, I'm not talking overall, still they could be B minus. But this is something I have seen. I'll see you tomorrow. Have a nice day.